All right, so we're going to take another look at transformations, but this time we're going to superimpose the coordinate grid on top of them. And what I have here is I just have a rectangle, and I've already traced it onto some tracing paper so I can make it a little bit easier to move it around. This is my x-axis, this is my y-axis, this is my origin here of 0, 0. And we're going to do this. I have another video that just goes through and explains the different types of motions. What we're going to do in this one is we're actually going to look at what are some of the nuances, or what are some of the things that occur when we start doing these different types of motions. So first and foremost, let's just do a reflection across the y-axis, which just simply means I'm going to flip it that way. Now I have my xy grid there, and I can line that up nicely, and then I can just make some points here. I can make some marks as best I can. This is more easily done with a mirror device, but for this instance I'm going to do it with the tracing paper, so that if you're trying to follow along you can do what I do in this instance. So what we have here is a prime, we have D prime, we have B prime, and we have C prime. So again, if you want to do this with a mirror device, this is what this is. You can see how when you look into the mirror, it gives you the reflection there. And I can position this so that the bevel for the mirror is lined up right there on the y-axis. I need everything else lined up. And I can see that I was just a little bit off with my tracing paper. Those are the actual locations there. And I want to be a little bit more accurate about this than I was previously, because I want to do a demonstration here for a couple different pieces and parts, just to kind of reiterate what's really happening with this. One of the biggest things to remember is that when we talk about rigid transformations, the idea is that the shape and the size has been maintained. Neither has changed any, right? Now what's also interesting to point out and useful is to look at the distance something is from your axis of reflection. In this case, we are 3.9 centimeters, 3.8 centimeters, something like that, from the y-axis. If we go the other direction, lo and behold, D prime is also 3.9, 3.8 centimeters from the y-axis. And that's true about all the pieces. So if we look at C, C is 8.3 centimeters, or the C prime rather, and C here is 8.3 centimeters. So not only did the actual size, not only are these two pieces right here congruent, but this distance from there to there, those two distances are also congruent. So whatever this distance is, let's call this spot right here, we'll call it K. KD is equal to KD prime. Those two distances are the same length. Now, how is that useful? Well, it's very useful when you think about this in terms of a real world application. What this means is that this box is the same distance away from the wall as its reflection would be on this box. So if you think about this in terms of whether this is a mirror and you're shining a light or an image into the mirror, what you're essentially talking about is that you have doubled the distance that you're looking at. And this is the whole principle of how compact telescopes work, is they're using mirrors to double the distances without creating the object to be significantly larger. You can use just a few inches, or a foot if you will, to create a telescope that's the equivalent of something that is extremely long, depending on how many times you move the image back and forth between the different mirrors. Now the other thing that also happens is, let's talk about, let's say that A here is let's say it's 3 units over, and say 4 units up. Well, A prime would be 3 units over and 4 units up, just in the opposite direction. That's the way that piece would work. So the same thing with B. If this was 5, 4, Well, this over here would then be 5 units over and 4 units up. The difference is it's in the opposite direction, so it'd be 5, 4. Same thing would be true if you were to move it down this way. If you were to reflect that box, I just roughly did that there, so here you would have D double prime, and here you would have C double prime, and B double prime, and A double prime. Notice some of us may have had some problems doing that reflection without the tracing paper. Like, well, why isn't this A? Well, because the whole concept of the reflection flipped its orientation with respect to the axis we were flipping across. D was the closest, D still has to be the closest. A was above D, now A is going to be further away, because the idea behind this is the distance from that axis of rotation has to be maintained. So it was 3.5 centimeters before, it still has to be 3.5 centimeters. I didn't draw it quite to scale, but I hope you can pretend with me on that piece of that, right? Again, these pieces still have to be congruent. I drew this as a rectangle, so we would assume that those opposite sides would be congruent, just like over here. So essentially what we have now are 3 figures that should be congruent and should be the same distance from their independent axes that they were reflected across. Now, how is that useful? Well, I mean, once again, you're still talking about these distances needing to be maintained. In another way, you're also talking about that you are creating parallel systems as well. So we still have the same area, we still have the same distance away, and this again was a reflection, right? Now, how does that change the points? Well, again, if this moved A 3 units over, A is still 3 units over. It was still 4 units up. This is still 4 units. Oh, it's down in this case, so it needs to be -4, right? It's just moving in a different direction. So B here would still be 5 over and 4 down in this case, right? Instead of in the other direction. So we just simply are going to maintain those exact same positions. So again, maybe you want to pause this one and say this would be 5 units over, and let's just say it is 3 units up. So what would C double prime be? Well, that would be 5 over and -3. So it's still being moved the same amount, but it's being moved in the opposite direction. Okay, so this is how reflections work. And we can even do this one down here. So this, if I'm going to reflect, so this was reflection 2, this was reflection 1. Now I'm going to reflect this one, so this would be a reflection 3. And somebody may be asking, you can do that? You're going to reflect a reflection? Absolutely you can. So this would be D triple prime. Wait a minute, would it? No, it wouldn't. That'd be C triple prime, right? This right here would be A triple prime, because notice A is the closest to the y-axis, and then this piece right here would be B triple prime, right? So what would this point be? Well, this point right here would be 3, -4. This point right here would be 5, -4. Actually, it's -5, and it's -3, because it's been moved. Both of the pieces have been moved in the opposite direction. So flipping across the y-axis changes the sign of the x, and flipping across the x-axis changes the sign of the y. So let's go back and let's restart this. But this time let's look at a rotation. Okay, I'm going to redraw my xy axis here. I'm going to redraw my figure, and I'm going to, for the sake of time, I'm just going to freehand this. So here's A, B, C, and D. I'm just trying to maintain everything as the way it was. So this was 3, 4. This is 5, 4. This one was 5, 3. Okay, and this, of course, right here would be 3, 3. That one's going to be kind of boring to look at, but we'll work with it. So we still have our x-axis and we have our y-axis. And here's my origin right here of 0, 0. Now, in this instance, let's rotate this. How are we going to rotate this? Well, we just need to take our original figure and we're going to turn it, right? So it's now going to move that way. So again, maybe we want to get out the tracing paper to help us do this process real quick, and I'm just going to make a mark here, and I'm reusing some paper. Hope you don't mind. All right, and there is A, B, C, and D. I always mark on my figure just because it makes it easier. So if I rotate that 90 degrees, right, I then have my image, right? So this is A prime, B prime, C prime, D prime. But how have the coordinates changed? I mean, it's still, in theory, it's still the same size and shape, right? But I've changed the orientation and I've changed the location. How has that changed point A? Point A is obviously not just 3 over and 4 up. I mean, if we did that as centimeters, that is definitely not moved over. It's easier to do on grid paper, but I'm purposely doing this on plain white paper just to kind of have the freedom and flexibility to play around with the values a little bit easier. Well, what's changed? Well, we rotated it around. So what actually happened is that we were actually switching those two pieces. It's now 4 over and 3 up. And then you can kind of see, if we follow this over a little bit, you can see it's lower than it was before. B is really emphasized, right? B has been moved over 4 and up 5, right? And if you notice those X values, they're the same. Notice here the Y values were the same. Here the A and B are directly, or should be directly above each other. The difference is that it's been moved left instead of right, so the X value has to be negative. C here, well, that's now negative 3, 5. And D, again, I told you that was the boring one, right? It's 3, negative 3, negative 3. So that was starting in that location and doing a single rotation. Let's do a second rotation, which puts it right here, right? So we get there, there, and there. Here's A, D, C, and V. And of course this would be double prime all the way around. Right? Now, again, the shape needs to be maintained. The size needs to be maintained. So again, pretend it's the exact same size and shape it was before. It needs to be the same distance from the origin as it was before. That distance needs to be maintained. That's actually something we haven't really talked about yet, has it? So this distance, remember with what we did before. So the distance from the origin to D still needs to be that same distance, right? If we go from B or go to A, that still has to be, well, there we go, still has to be maintained. Well, notice what we're creating there, right? If you were to look at this, let's go from origin to A and then down here to the x-axis, right? You have a right triangle with the x-coordinate, the y-coordinate, and then, since this is a rotation, we're kind of creating a circle, so we'll call it R for a second. But if it's a right triangle, that means that x squared plus y squared equals r squared. Well, think about what you're doing now. That r has to be maintained. That distance away from the axis or the point of rotation needs to be maintained, right? So you still have y and x. The difference is that they're changed, right? So that by a result of that rotation of that r, that distance from the point of rotation needing to be maintained for all the points, this point switches. So now you're dealing with this being negative 4 and this being 3. Because it's going to be, just going to switch those two pieces. So once again, when you go down to here for A prime, once again, you're flipping them. So now it's negative 3 and negative 4. Because you still have that right triangle with that radius that still has to be maintained. Let's now look at that. Look at what A is when we do 2 rotations of 90 degrees. versus 2 reflections across the 2 major axi. -3, -4. -3, -4. Isn't that something? 2 rotations of 90 degrees is equivalent to 2 reflections across the x and y axis. It gives us the same figure. All right, and we could do this again. We would have another shape over here, and then we could rotate it one more time and we get back to the original shape. Just like with the reflections, 2 reflections in different directions give us the same shape as a rotation of 180 degrees. Now, this is not the only instance where this occurs. This is just one of them. There are other things you can be doing with this. I really encourage you to play around with these different types of rotation transformations and seeing what all you can come up with, even to the point of maybe coming up with some other regular figures and seeing what else you can do with regular figures. An easy way to play around with these is to cut a bunch of these out and just kind of move them around a little bit and see what you can do. Maybe you want to create a non-regular figure. This, and by the way, this leads you directly into tessellations, where we start taking the figure and we start moving it in different places and different parts. Okay, so I encourage you to kind of play around with that as well. See what all you can do as you move the parts and the pieces around. All right, take care.